Okay, yes. I'm Vitja Beltram. I work with Miha and Giga, and I will talk about charge-active nematics. There will be some concepts that will be similar to the ones Jeffrey presented, and also some similar pictures, but I hope I could present them in a bit different way so that you can understand them more. But today I want to tell you a story about how one could, in principle, build a machine that could produce electricity. So if one could build a machine out of charged active nematics that could produce electricity. But first, let's start by defining our system. So on one hand, we have active nematics. I will explain them a bit more in a minute. But basically, these are nematic liquid crystals that consumes energy that transforms energy from surrounding into the motion. So we get this chaotic movement of these topological defects that we also heard about. In this system, we want to add ions. So it's a bit of a continuation, I guess, of Jeffrey's work. So we get charged active nematics, and we want to explore how these charges and couplings between ions and nematics affect these active nematic liquid crystals. So yeah, what are active nematics? These are nematic liquid crystals. So we have this orientational order that we describe with director field, but because it has a head-tail symmetry, so it's not really a vector, we have to introduce this Q tensor, which is a second-order tensor. And in this system, we want to include activity. So how we do that? We have in mind small bacteria, small elongated objects that are swimming at the very low Reynolds number. This means that the inertia is neglected. And in that regime, the net force that this particle exerts on the fluid has to be zero. So the first non-trivial order, it's a dipolar force that the particle exerts on the surrounding fluid. So if there is just one molecule, this forces cancels out. But if there is some deformation in the system, like here, so we have some, as we seen before, there is the nematic molecules aren't aligned perfectly, but they have some deformation, some band deformations. There is some net active force acting on the fluid, modeled as with this equation, and such force actually destabilizes this deformation. So the deformations actually grow in time. So the system is not stable, and if there is even a slight deformation, it will extend, and it will extend to that point that it will actually create a pair of topological defects. So plus and minus 1/2, because topological charge is conserved. And we describe the topological defect with topological charge, which means just how many times the director rotates when we encircle the topological charge. So in upper example, the director turns by half. And as Jeffrey mentioned, because there is frustration in the director orientation in the core of topological defect, the nematic order melts, and we have isotropic liquid in the core of topological defect. Okay, and now if we would use this active force and calculate velocity profile around plus and minus 1/2 defects, which are the most common ones in active nematics. That's why I will mostly be picturing them. We see that plus 1/2 defect is actually propagating, can self-propagate, and minus 1/2 stays doesn't self-propagate because of this trifold symmetry. Yeah, okay. And with different confinement, with changing of activity, we can have very different dynamical regimes. So for example, on the top left picture, we can see on the left, there is, we can have some net flow, we can have these defects dancing in the spirals, or we can actually get this active turbulence, which is chaotic movement of topological defects at low Reynolds number. I just want to also to add that this active nematic model is also used to simulate the growth of bacterial colonies or the epithelial tissue, movement of cells in the epithelial tissue. Okay, now let's try to combine those systems. So active nematics and ions, as Jeffrey also mentioned before. So on one hand, we have this nematic order, which we describe with Q tensor, and velocity field V. On the other hand, we have ion density and electric potential. So ions couple to each other, but they couple also to a nematic order via solvation, which is the same as ion partitioning that Jeffrey mentioned, and ions couple to nematic orientation via flexoelectricity. So let's look at these two couplings a bit more. I hope this will not be too similar to Jeffrey's. So solvation, and let's focus first to the passive case. I will go a bit more faster here. So basically, yeah, in the vicinity of topological defect, we have a border between isotropic liquid and the nematic liquid because of this melting in the defect core. And because different ions solve differently in different fluids, we can actually get a charge separation at the boundary if we look at the red curves, where the solid one is for negative ions and dashed one is for positive ions. And so we can actually get like electric double layer, but this time in the bulk. So we don't need actually any surface. This can happen in the bulk. Yeah, and if we look at that a bit in this maybe more schematic picture for this plus 1/2 topological defect. So because of this changing of nematic order, we get some effective potential to which ions couple. So ions get actually attracted to the core of the topological defect. In this case, there are plus ions, positive ions, and in this plot that Jeffrey calculated, there are negative ions. But the concept is the same. So let's look also at the flexoelectric coupling. So again, the flexoelectric polarization comes about when we have nematic molecules that have electric dipole and are also anisotropic shape. So when there is some deformation in the system, the molecules align in the same direction. So we get some macroscopic polarization, which we model with this expression. And around plus 1/2 defect, the flexoelectric polarization is like this, if we calculate with this expression. And this produces electric field, which actually separates positive and negative ions. So we, in around plus 1/2 defect, because of flexoelectric polarization, we have separation of positive and negative ions. And if we look at the, if we calculate that more carefully, we get such distributions around plus and minus 1/2 defects. Okay, now let's go to the active nematics. I'm doing simulation, so I'm calculating, solving these 4 equations numerically on 2D square grid. So we have dynamic equations for nematic orientation, where H is molecular field and S is the coupling between velocity and nematic orientation. So if there is velocity in one direction, also nematic molecules will try to align in the same direction. Then we have Navier-Stokes equation for material flow, where there is equilibrium, stress tensor, viscous one, and the active one I showed at the beginning. Then I have Poisson equation for electrostatic with flexoelectric polarization, and continuity equation for ions, where J is ion flux containing advection as well as diffusion. So let's see how what will activity do to such system. So for in this case, we are looking at +1/2 defect. So these two pictures, first two pictures I showed you already before. So because of solvation, we have some localization of positive ions in the vicinity of the defect core. But because of activity, this +1/2 defect is actually self-propagating. So we have some propagation of this defect, and because ions are coupled strongly to nematic orientation, we actually get some ion current in the system. If we do simulations more carefully, we can, these are the results. So in -1/2, the ion current is negligible, but on +1/2, we get some ion current. And when there is ion current, we also have magnetic field. So I'm calculating magnetic field with these equations, with this equation in 3 dimensions, and then I'm plotting here only the component in this plane of the nematic, and with the red color, it's represented the component that goes out of the plane, and with black the one that goes into the plane. So it's like we will have a very short wire with the in this case. So let's move to the flexoelectric coupling. Here again, so because of flexoelectricity, we have a separation of positive and negative ions, and because of activity, this defect is self-propagating, and we get actually dipolar ion current. Yeah, and if we look at the pictures again and the magnetic field, we get this quadrupolar symmetry of magnetic field. Okay, and now let's move to the ion-doped active turbulence. So this chaotic movement of topological defects. Here I have a system that is confined to the circle. I have boundary conditions for nematic that is planar, so the orientation of nematic at the boundary is perpendicular to the normal. Then velocity at the boundary is 0. I have a constant voltage regime with the 0 potential at the boundary, and I am conserving the number of ions, so there is no current through the surface. Okay, so here are the results. Here with the green arrows, I'm representing the velocity field in such system, and with color map, I'm representing the nematic order. So when there is a decrease in nematic order, we know that there is topological defect. So here we see these dots are the topological defect. Here above this nematic order, I'm plotting also the director field. Okay, and now in such system, we have ions. So and because ions are strongly coupled to nematic orientation, we have this chaotic movement of ions around. We can clearly see where there is -1/2 defect or +1/2 defect, and we can see that +1/2 is really moving. They are being created in pairs. They are being annihilated in pairs. So yeah, it's a lot going on. And if I plot on top of that electric current, we can see how it's localized around +1/2 defects. It's changing the magnitude, the orientation, and it's chaotic. And then magnetic field of such electric current looks like this. So again, we have a localized magnetic field around these +1/2 defects, and because some are getting created and annihilated, also the overall magnetic flux through such system is changing with time. And because of that, we are arguing that in principle, one could build a system out of charged active nematics that could produce electricity. So to conclude, because of solvation and flexoelectricity, we have some interesting distribution of ions around topological defects. And because of activities, these topological defects are moving, creating interesting distribution of electric current. And this creates magnetic field that creates magnetic flux that changes in time and could in principle induce some voltage. Thank you.